All right. Whew. Let's talk a little bit about chemical equilibrium. And this is kind of a new concept. I guess all of them kind of a new concept. But this is, to this point, we've been thinking about reactions and reactants going to products. And theoretically, we think that, at some point reactants run out, and that's as many products as I can get, and that's how reactants work. Except that's not quite right. Some reactions work that way, but most reactions actually live in some sort of equilibrium. So let's get to that point. Okay. So we're going to see in this section that reactions don't necessarily always go in the forward direction from reactions to products. Sometimes they'll go backwards from products to reactants. And basically we label these as kind of a forward reaction, reactions to products, and then a reverse reaction, reactants to, or products to reactants. Okay, so that's what we mean by a reversible reaction. It can go forward or it can go backwards. Okay, in reverse. Okay, so most reactions, especially like in your body, exist somewhere between reactants, not between reactants and products, but with some reactants still around and some products still around. Okay, and your book explains it like a basketball game. That on the court you always have the 10 players on the court, 5 on each side, but during the game, the people who are sitting on the bench can go into the court, and the people on the court can go to the bench. But there's always 10 people just that are playing, okay? But they can switch in and out. That's what they describe equilibrium as, and it's kind of like that. That you get to some point where the amount of reactants being produced is the same amount as the amount of products being produced, and the rates of the reactions are the same. And so basically you get to this constant, this balance, and that's where the equilibrium is. Okay. So in science, in nature, things work to lower the energy, and the more stable things have lower energy. So in a reaction, if that lowest energy exists somewhere where there's a certain number of reactants still around and a certain number of products still around, your system's going to be in that state. Okay. If the lowest energy is to make everything product, it's going to be in that state. If the lowest energy is going to keep things as reactants, it's going to be in that state. Okay, so most reactions that exist in nature exist in this thing, this equilibrium, where there's some products and some reactants still around, and it's just back and forth. So we've got the little diagram, the graph on the right, which basically shows us kind of the percent composition of products, where we see that equilibrium, there's some reactants and some products, but we don't have all reactants or all products. It's some mix of both. And then if we do something to the reaction, like we heat it up, or we cool it down, or we add things to it, that equilibrium is going to shift, and we're going to talk about that in the next section. Okay. But when we have a reaction that can go both in the forward and the reverse direction, we write it with double arrows. Instead of just one arrow showing reactants to products, we do 2 arrows, one in the forward direction and one in the reverse direction. And typically we do these as half arrows, where we only draw the one side of the arrow. But that's kind of what's happening here. Okay, so that's what's going on. In this balance, or this equilibrium reaction, we have hydrogen gas and iodine gas combined to form hydrogen iodide gas, and it lives in some equilibrium where we have some reactants and some products existing, and reactants are going to products and products are going to reactants, but at equal rates. So the amount of reactants and the amount of products is constant. That's what equilibrium is. Okay, so if we start only with H2 and I2, the reaction's going to go at a certain rate, relatively quickly usually, to make product. Once some product is formed, the reaction will go backwards also. Okay? And there'll be this kind of, I don't want to say competition, but there'll be a forward reaction going and reverse reaction going. And if you started with all H2I2, that forward reaction is going to be the dominant thing for a while. Until you get to the point where you're nearing equilibrium, where you're nearing the point at which the amount of reactants and the amount of products are going to stay constant. Equilibrium. So equilibrium occurs when the rate of the forward reaction is equal to the rate of the reverse reaction. Right? So the rate of the creation of products is equal to the rate of the creation of reactants. And when that happens, the concentrations or amounts of each of the reactants and each of the products are constant. So the reaction's still happening, but since they're happening at the same rates, the amount of reactant that's producing product is the same amount of product that's reducing reactants. So the forward reaction is the same rate as the reverse reaction. So overall, everything's staying constant. Okay, so there are going to be times when the reactants are favored, meaning that there's going to be more reactant than products. There's going to be times when there's more product than reactant. So if there is, if at equilibrium the concentration of products is greater than the concentration of reactants, like we see in this one, it said the reaction said to favor the forward direction, the forward reaction, or the products. So we can say, in this case, we can see that there's more product than reactant. So we say that the reaction favors the products, or the reaction favors the forward reaction, because that's the one that takes us to products. If it's the other way, where there's more reactant than product, then we say that the reaction favors the reactants, or the reaction favors the reverse reaction, right? The production of more reactant. Okay, so this is more reactants than products, so that's when we favor the reactants, and this is more product than the reactant, and that's when we say that reaction favors the products. Okay, so we have this thing called an equilibrium constant, and well, we're not going to go too far into it here because it's a little bit more complex than we're actually making it. We're simplifying it. The equilibrium constant gives us a kind of the ratio of products to reactants. Okay, the amount of products formed versus the amount of reactants that are still around at equilibrium. So it gives us some measure of if the forward reaction is favored, or if the products are favored, or if the reverse reaction and the reactants are favored. If K equilibrium is, in this case, if it's greater than 1, that means there's more B than A. That means we can say our reaction is A to B. That means there's more products, and that would mean that we're favoring the forward reaction or the products. If K equilibrium is less than 1, that means A is bigger than B. It means we have more A reactants than we have products. That means the reaction favors the reactants or the reverse reaction. Okay? What does it mean if K equilibrium equals 1? Well, that simply means the amount of reactants and products are the same, so it doesn't really favor either. It's kind of equal between the two. Okay? That's equilibrium.